Assalamualaikum and very good morning to everyone. How are you? I hope you guys are in great condition and excited as usual to learn our new chapter. So today we start our new chapter, Radio Digital Modulation. We have finished chapter 4 on pulse modulation. So this is the continuity. Okay, before we learn about analog modulation, okay, where we will use higher frequency signal to transport or to carry our information signal. Okay, and then in pulse modulation, we learn how to produce or how to convert from analog to digital signals, where a series of PCM codes or binary signals are produced. So this in chapter 4, and radio digital modulation is when the binary signals are used to modulate the carrier. Okay, in chapter 2 and 3, the continuous or the analog information signal is used to modulate our analog carrier. But with radio digital modulation, the digital signal is used to modulate our analog carrier. So this is our mind map. The very fundamental of radio digital modulation are three modulation techniques, which are ASK, FSK, PSK, means amplitude shifting, frequency shifting, and phase shifting. We'll start with the basic principles, as usual, with the general equation of these techniques, the waveform, and also the spectrum. And then from the spectrum, we can evaluate the bandwidth performance of these techniques. And then we look at the generation and detection circuits, okay, for asynchronous and asynchronous methods. Okay, and then there's one new thing that we will learn here, which is bit error rate. We didn't learn about bit error rate in previous chapters, because bit error rate is the another metric, performance metric that is used to represent the system's performance apart from SNR. Yeah, but this especially for digital modulation. Right? So it can be understood from the term, which is bit error rate. So since it's bit, it belongs to digital modulation. In analog modulation like AM, FM, there's no bit error rate. We have SNR. SNR is more general term, can be used for analog and digital, but bit error rate only for digital. Okay. And then we'll look at a special concept which is known as multi-level shift keying. Okay, so this multi-level shift keying actually applicable for all ASK, FSK, PSK, but we'll focus on multi-level phase shift keying, especially the QPSK, quadrature phase shift keying. Okay, we look at the equation, constellation diagram, how to generate and detect QPSK signals, and also the bit error rate performance. And under multi-level shift keying, we'll also learn about new concepts such as baud rate and spectrum efficiency. Okay, so for this first part, okay, I will separate the lecture into two parts. Okay, for today we will learn on the basic or binary shift keying, which is ASK, FSK, PSK. And in our next lecture on another day, we'll learn about multi-level shift keying. Okay, but it's important to understand this basic shift keying before we go deeper into multi-level. Okay, so what we have learned from chapter 4 are the pulse signals, but we didn't learn about modulating the pulse signals that we generate, eh, from the A to D process or from the line coding. We don't modulate. We just stop at line coding. We can change to whatever format. Okay, so if we transmit without any modulation, then it's called baseband signal. Okay, but practically, especially when we consider a certain medium such as air, that is analog medium. Okay, it's not practical to use baseband signal. So in this kind of situation, especially for analog medium, we have to modulate the carrier. We need to shift our information signal from the baseband to the frequency that is suitable for the medium. Okay, so here it says digital signal can also be transmitted through free space if the analog carrier signal is used. So this is one practical application that requires the modulation of analog carrier in free space. So three basic techniques are amplitude shifting, frequency shifting, and phase shifting. Okay, so in my further explanation, you can notice the similarity in terms of the concept with AM, FM, and PM. Okay, so historically, the term shift keying, okay, refers to the breaking of circuit, yeah, to represent 0 and 1. Yeah, so the control of circuit breaking is used. They use key, yeah, to shift the current value from 0 to 1. Okay, so the concept is very similar to analog modulation, where the modulating signal vary the carrier's amplitude, frequency, or phase. Okay, but for this chapter, our modulating signal is a digital signal or binary signal. Okay, in this case, binary signal. So instead of continuous, our information signal is in the form of series of pulses like this, represented by this square series of bits 0 and 1. Okay, for ASK, um, there is signal or carrier signal only presents at bit 1. Bit 0, no carrier signal. Frequency shifting, okay, there are two values of frequency that represent bit 0 or bit 1. Okay, so and also for phase, only two phases represent bit 0 or bit 1. Okay, if you notice, it's much in terms of the changes to our carrier signal is simpler because it involves only two levels. Two levels of amplitude, two levels of frequencies, or two levels of phase. Okay, since we are only interested on this 0, low level, and 1, high level. Okay, so this is just to show the more complete block diagram of digital transmission system. Okay, so what we have learned from chapter 4 is up to here. Yeah, this one, RZ and RZMI, so the line coding. And then, but if we want to transmit over free space, for example, or even wired, and where we are supposed to follow the wired medium frequency, then we have to modulate the carrier. Okay, so here with digital modulation, then we have this ASK, FSK, and PSK. Okay, so the concept is very similar, which is the carrier shift the baseband signal, digital data, to a higher spectrum around the carrier signal. Okay. Okay, we will look at the first we start with the very basic, which is ASK. Okay, with amplitude shifting, so here is the spectrum of our carrier. So our carrier is represented by just high frequency sine, continuous signal. Okay, and then our information signal is digital signal. Eh, can be represented by this unipolar bit series. Okay, and this is the spectrum of our square wave. And then when we multiply these two, we modulate these two, the carrier signal will be changed based on the information signal's amplitude. You can see when there is bit 1, okay, we have the carrier signals here. When it's bit 0, no carrier. Okay, so the string of pulses from digital signal will change the amplitude of the carrier signal. So we can see here, okay, modulation causes our information signal or the baseband signal shifted to the area around our omega C, our carrier. Okay, so this ASK is also known as on-off keying or interrupted continuous wave, because you can see that instead of just continuous, bit 0 cause interruptions to our continuous carrier signal. Okay, in terms of the generation of ASK signal, yeah, we can generate just by multiplying our carrier with our um, digital or binary signal to produce ASK signal. If our signal, the unipolar signal, is represented by this information signal VMT equal to half plus 2 over pi cos omega mt minus 1/3 cos 3 omega mt plus 1/5 cos 5 omega mt. So up to the fifth harmonics we use here in our equation. And our VCT is EC cos omega CT. So we multiply these two. Okay. So when we multiply, what we can see here, what can we observe? We have this EC cos omega CT term, half EC cos omega CT, and then 2 over pi EC cos omega CT cos omega m. And then we have this third harmonics also and fifth harmonics multiplied with our VCT. So we have the carrier component, the double sideband, and also the double sideband components. So the double sideband components is centered around FC plus minus FM, and then FC plus minus 3 FM, FC plus minus 5 FM. Okay. So in terms of bandwidth, depends on the receiver's requirement on the shape of our square wave. Okay. So if we consider up to fifth harmonics, that means that we want the shape to be quite sharp lah, in terms of the edge, the tajam, quite sharp. Then we have to consider a higher harmonics. Let's say we consider up to fifth harmonics. Then, okay, we have to include up to 5 FC lah, plus minus FM. Okay, so then the total bandwidth, considering up to fifth harmonics, will be 5 times 2 FM, where 2 FM is our bit rate, FB. So if we do not um, consider the requirement of the square shape, if the square shape is not that strict, for example, we just want what is important for our receiver is that we know that it's bit 1 or 0 enough. We doesn't matter the shape of the signal. Then in this case, we can take the minimum, which is just 2 FM. Then bandwidth ASK, considering only the fundamental, FC is equal to 2 FM, which is equal to FB. Okay, so the, here, since our square wave, our digital signals in binary uses square wave, so we have this concept of the required square shape requirement. Okay, so to calculate total bandwidth, you need to pay attention to the question up to what, up to how many harmonics that should consider or should be included. Okay. Okay. So we look at the generation and detection. Yeah, it's quite simple. So basically, you can use multiplier. Okay, this filter is to limit the frequencies of our FM up to whatever harmonics. And then we multiply with our carrier. Then we get our ASK. We can also use on and off switch. Okay, where our VMT that produce 1 or 0. Okay, and this 1 or 0 bit will control our switch. So if it's 1, the switch will be on, then only VCT will be, and our carrier will be transmitted. Okay, otherwise, if it's 0, the circuit will be broken and circuit is cut, and then there's no carrier frequency. Okay, for detection, we can detect using envelope detector. This is very similar to our full AM signal. Okay, and then you can also use coherent detector. Okay, by multiplying just our ASK, the signal, with the locally generated carrier. Okay, and then we will look at the bit error rate. Okay, so in digital communication system, bit error rate is very popular performance metric. Okay, so what is bit error rate? Bit error rate is the error error bits, basically error bits divided by total received bit. Okay, so let's see here. It says the differences between the send and receive bit. So the differences between the send and receive bits, this one is our error bits. Okay, so bit error rate is the error bits, erroneous bit divided by total bits. Let's say if our transmitter send 10101110, let's say this how 3 4 5 6 7 8 9 10. Okay, this 10 bits, and then this is at the transmitter. At the receiver, receive 1 0 1 1. Okay, so if we compare how many errors here, okay, 1 0 correct, and then 0 0 supposed to be 1 1, but we receive 0 0. Okay, the rest I think okay. So we have two, and these are two bits that are different, and this 1 1 1 0 0. So you have two error bits. Okay, so bit error rate is 2 divided by 10, which is 0.2. So out of 10 bits that we send, 2 bits are error, and we have 2 error bits. Okay, so this is the actual, we call it actual bit error rate. Okay, so we compare the bits that we received and the bits that we sent. Okay, but practically, okay, it's very difficult, eh, to measure actual bit error rate, because, okay, the requirement for, okay, current, system, the error is quite high. For example, in optics, the requirement is 10 to minus 9 or 10 to minus 12, okay, bit error rate requirement. So meaning that we, and this, for a system to be accepted, okay, it should have only one error out of 10 to the power of 9 bits. Okay, so to produce, this, to measure, bit error performance for this very high number of bits, 10 to the power of 9, 10 to the power of 12, it's very time consuming. Okay, and it requires a lot of resources. So what we do, in the academic world is that we estimate the bit error rate. Okay, that's why, okay, and the estimated bit error rate is also known as the probability of error. Okay, the estimated bit error rate. Okay, this is also known as probability of error. And this estimated bit error rate or probability of error depends on certain factors, such as the modulation techniques and SNR. So because, we estimate, yeah, the bit error rate, so, there's, it's very difficult to come up with one equation or probability equation that represents, that is applicable for all modulation techniques. So that's why certain modulation techniques has its own, bit or PE equations. Okay, and apart from modulation technique, it also depends on the SNR. So given SNR, we can estimate our bit error rate, and this SNR depends on the energy per bit and the noise power spectrum density for single-sided. Okay, so for ASK, the probability of error follows this equation, which is half error function square root of EB over 4N naught. So this is the formula to calculate PE, probability of error, or estimated bit error rate, okay, for ASK. Okay. I shared with you the, one appendix on this error function table. Okay. So the error function can be solved by referring to error function table or use a simplified approximation equation. So this is the, error function equation. Okay. And for x, larger, much larger than 2, we can simplify this error function to this equation. Okay, exponential minus x squared, x minus x squared divided by square root of pi times x. Okay, so in your final exam, you can be given either the table or, they can just give you this equation. So if they give you equation, meaning that the x that you calculate should be quite large, larger than 2. Okay, so these are the values from the error function table. Okay, So we just calculate, find the x, and then look what is the value of our error function for a given x. Okay. All right. So I'll stop here and for this part one of today's lecture, and I'll continue in the second part for FSK and PSK so that our video won't be too long.